time this morning. Today I'll be talking about my PhD research, which is characterizing technology for simultaneous thermal control and aerovalization of spacecraft and surface habitats. First, I'd like to introduce my committee, which is chaired by Dr. James Navity of the Bioastronautics Department, followed by Dr. Norman Clark and Dr. David Cost of the Bioastronautics Department. I have NASA representation by Dr. Daniel Barnett from Johnson Space Center, and then I have biology advisor, Dr. William Lewis from the Department of Technology. And for some of you who don't know who I am Emily Batula, and I'm currently pursuing a PhD in bioastronautics here at the University of Colorado. Before that, I was at the University of Michigan doing my undergrad in mechanical engineering and my master's in space engineering. But I always wanted to do more of the human side, which led me to here. So that's kind of my motivation of why I'm doing a PhD, but for the research part of it, we're going to Mars. And in order to get there, we are currently looking at using the moon as a gateway. And we are also looking at utilizing our platforms below Earth orbit, including the International Space Station, which is currently the longest and human-inhabited orbital spacecraft. And it has developed this range of environments that are acceptable for human habitability. But interestingly enough, even though this has set the standard for human spaceflight, NASA has already acknowledged that there are some gaps in the knowledge and technology if we are hoping to get to Mars and further into space. So in particular, for the environmental control and life support systems, so all the things that help support us humans in space, there are some issues with the current technologies. So my research is going to be focusing on the carbon dioxide, so the aerovalization, carbon dioxide removal, and oxygen provision, and the thermal control side of things. So I'll be focusing on these four aspects. Currently on the International Space Station, we have the Seizure system, which pulls CO2 out of the cabin environment using the zeolite sieve. But unfortunately, that molecular sieve can break down, and that dust can propagate through the entire system, causing failures by way of stopping up the pumps, contaminated filters, things like that. And previously resulted in multiple failures per year, which then results in crew time and consumables. But that concentrated CO2 eventually flows into this body system, which then, with the help of hydrogen, is then reduced down into methane and water. But unfortunately, that system operates at an extremely high temperature and has hydrogen as a consumable because right now that methane is vented off in the space of the waste. It's not used. And if you look at the Sabatier equation, we actually have a relatively low return of oxygen. But the water that is produced by the Sabatier system is then transferred over to the oxygen generation assembly, which is then broken down into hydrogen, fed back into the Sabatier system, and oxygen, which is then provided to the cabin environment. But what we've shown here is that it requires multiple systems in order to have that CO2 to oxygen turnover. So it's got to be a better way. And in fact, NASA actually did suggest a biological solution, which is looking at using algae or bacteria in order to close that carbon loop and provide oxygen production. And we can see that by just taking a look at the photosynthetic equation that we all probably read in second grade. You have the input of CO2 and you have the output of oxygen and some carbohydrates. Some pretty good things about this particular solution is that it's operational at ambient temperatures. You've probably seen algae growing in ponds, streams, puddles out in the open. We have high photosynthetic and volumetric efficiency, meaning for one particular footprint, you could have an extremely dense culture, while you may only be able to produce so much wheat or corn in that same footprint or volume. And it's highly adaptable and multifunctional. As we can see in this figure here, you could potentially produce clean water or even edible biomass. So that takes care of the air revitalization side, but also the system could take care of that thermal side that I'm interested in. Because currently on the International Space Station, we have water cooling loops that take metabolic equipment heat from the cabinet, transfer it over to the heat exchanger, which is then transferred over to the ammonia loops and ventured off into space. So that cold water, now cold water, can then be returned to the cabin and allowed to absorb more heat. But unfortunately, this system is not tolerant to microbial growth. It produces biofilms, which clogs up our pumps and reduces the efficiency of the heat exchange services. But what if we did have a system that actually was tolerant of that microbial growth? So here is a concept drawing by Mark Cohen, part of the Water Walls project, in which he took algal bags and lined the inside of a Bigelow 330 spacecraft and used it for passive thermal control and air revitalization. But if you read their document, they said, we're interested in thermal control at this time, but we just don't have the money or the time and the resources to do that. Well, in a PhD, you at least have plenty of time. So, with the benefits of combined power and air revitalization thermal control, we can see that we potentially have a reduction in mass power volume compared to the current standard for air revitalization and thermal control. We also see that it's responsive to environmental conditions. Because if you look back at that photosynthetic equation, you can see that if you increase your carbon dioxide provision, you eventually would get an increase in oxygen. And so if you think about it, if you are exercising, you're respiring more carbon dioxide, and actually I typically need more oxygen when I am exercising. So it is a positive correlation. We also see that there is an increase in oxygen from CO2. Again, looking back at that photosynthetic equation. And we have additional functionalities that we could take advantage of if we look back at that image from before. So the research that I'm going to be presenting in the next couple hours, we'll be focusing on these particular inputs and outputs. I will not be considering drinking water, potable water, gray water, or anything with solids. So my research hypothesis is an algal system's oxygen provision, carbon dioxide reduction, failure modes, and adaptability to the environment make it feasible for long duration space flight when compared to the current air revitalization and thermal control in ISS. So in order to answer this hypothesis, I came up with these questions. So how will an algal culture respond to temperature swings? Now, this is the algal culture itself. I'm not looking at the system right now, but this is cell physiology. So how will that respond to temperature swings? How will that respond to variations in CO2 concentration in the cabin? But then also, how will the system as a whole support algal growth in this combined system? And as well, respond to temperature swings and carbon dioxide swings. And then finally, what are the failures of the system? So if I have a great system but it fails every month, it's not actually worth its weight. So in order to answer those research questions, I developed the following objectives. So investigate the reliability of the algal bioreactor system, determine the environmental influence when trying to reduce CO2 and provide oxygen while using it for thermal control. Taking a look at the effect of using the algal system for air revitalization in that dynamic CO2 environment. Characterize the heat transfer across a non-porous membrane in order to support a algal photobioreactor. Finally, develop a benchtop system that allows gravity-independent study of algal culturing. And then, actually, finally, determine first-order feasibility of an algal photobioreactor system as opposed to looped CO2 reduction, oxygen regeneration system. So in order to follow these objectives, I conducted the following research. So first I took a look at the failure modes. And I want to bring about the point that I surveyed a bunch of different failure modes, but the ones that I will be presenting here today are really only important to the research that I conducted, but also the system that I eventually developed. So if you are interested in the other ways that algae can fail or the system can fail, please read my paper. But in the literature survey that I conducted, what I did see is that, especially in batch culturing, there's this very predominant trend. And what happens is we have this lag phase, so over the first couple of days, the cells are acclimating to their new environment. And then we have exponential growth, and then stationary death. So in the exponential growth phase, what happens is the cells are utilizing all of their inputs to their best abilities. They're eliminating inputs, and they are basically cranking away as efficiently as possible. What happens is, as the culture becomes denser and denser, eventually you start to have a limiting input, and which can then result in the stationary phase. Now, if you don't address that limiting input, eventually you will hit your death phase. So in the case of my research, I was most interested in the temperature, the CO2, and the illumination. So you can see here with this black ball curve that as you increase illumination, you actually can over-illuminate your culture in regards to how much CO2 you're providing or how much temperature your environment has, or how warm your environment is. And we see that there is growth across the entire regime. It may not be optimal, but it is there. Also, when we're looking at how we're going to implement this system in the spacecraft environment, we have to be cognizant of the fact that we are going to be working in a microgravity environment. Because it's microgravity, this means we can't be using sparge systems or bubble systems. And so we will need to rely on mechanical pumps, mechanical systems or pumps in order to mix the system or keep the nutrients flowing through. But it turned out that the type of pump actually matters as well. So if you want to keep the viability of your culture up, you need to make sure that you are selecting the right materials as well as the right hardware. So ultimately what I concluded is cultures are tolerant of optimal conditions. We saw that even though they may be operating at a lower temperature, they're still growing, they're still photosynthesizing. We also saw that your material and your hardware selection is very important in order to support the viability of your culture. And then in my personal experience, as well as experimentation, I saw that cleaning techniques are also extremely important. In this case, I ended up starting to use a hydrogen peroxide solution in order to clean my equipment instead of using the typical hydrochloric acid bleach rinse, just because of the nooks and crannies that I had in my system. I found that it was actually leaching bleach into the culture and turning off my culture. So, and complications. So then we'll go ahead and move into more of the physiological side. So my ultimate experiment is this comprehensive bioreactor unit. So we're going to look at the simultaneous aerovolization thermal control. And in order to do that, I realized that I really should be splitting up that system into these smaller parametric experiments in order to better understand each aspect of the photobioreactor system. And using those results and lessons learned to eventually feed into this larger bioreactor. So first we're going to be focusing on the temperature cycling. So we saw this figure before on the left, which is the International Space Station cooling loop diagram. But if you can imagine yourself as a little water molecule in that cooling loop, as you travel through the cabin environment, you will start to absorb heat from the surrounding area. And then eventually you will move past the heat exchanger, release all that heat, drop that temperature, and then return back to the cabin environment, which is the temperature cycle that you see on the right. Now, If you weren't a water molecule that's an algal cell, you would experience the same type of cycling. So we need to look and see if that's extremely stressful, and if it is stressful, how does that influence the CO2 to oxygen turnover? So I developed a Peltier cooler system, which is controlled by a thermocouple in Arduino. I also have a fiber sting, which is a fiber optic dissolved oxygen probe and pH probe. And with this combined system, I was able to replicate these temperature swings. Now, these temperature swings are actually much broader than the typical lower temperature cooling loop, or the LTL, which is what is used to control the cabin environment of the International Space Station. And the reason I included much higher temperatures, so in this case, instead of just stopping at 14 degrees C, I went all the way up to 27 degrees C. That's because I wanted to also include cabin environment and test the most extreme envelope, operational envelope for this algae. So while I have these 4 different test cases, I will only be focusing on these 2. The nominal is what I will be calling the control, and then we also have the temperature cycle. So the hypothesis is that the temperature cycle culture will have reduced oxygen production rate, cell growth rate, photosynthetic yield when compared to the constant control. But in talking with my advisors and also looking at my experiment operation protocol, I realized that I had 2 confounding variables. One of them being contamination status, and one of them being daily nutrient addition. So in terms of contamination status, if bacteria is present, or other cultures or other species besides chlorella, there's a possibility that I would be characterizing the effect of temperature cycling on bacteria, not on chlorella, or temperature cycling on any other species present, not just chlorella. And then in terms of the daily nutrient addition, there could be a potential advantage that I'm giving those cultures that are receiving those daily nutrients. So I needed to make sure that I isolated each one of these different variables. Unfortunately, I could not conduct the xenic with daily nutrient experiment because inherently, as I added the daily nutrients, I was adding contamination. So here's just a snapshot of the oxygen production of an xenic culture. So you can see that it is producing oxygen. Now, before each one of my cases, both the control and the temperature cycle cases, I went ahead and ran a Bristol's baseline case. So running these experiments with just Bristol's media present, no culture present, so that I could remove and isolate the oxygen produced by the culture instead of oxygen contained in the Bristol's. So the next 3 slides are going to be looking at the xenic test cases. Here, the oxygen generation rate is studied between the xenic case as well as the contaminated cycle case, so those cycles. But what we see here is that contamination status doesn't seem to have a direct influence on oxygen production rate, which, if you think forward, that means that we may not need such stringent cleaning protocols in order to produce oxygen for the cabin environment. Also, the photosynthetic yield was studied. Photosynthetic yield is a proxy for cell health. It's measured on a scale from 0 to 1, and it looks at the photosynthetic capabilities of the cell. And what we see here is at the beginning, the cycled case is relatively happy, but over the next couple of days, it drops dramatically. And it's hypothesized that it's because it's in an acclimation stage. But what we see is that over the next couple of days, it actually recovers and is within the range of the control cases. For the growth rates, we do see that control versus cycles, as well as the contamination status, does matter for growth rates. And then for the next 3 slides, now I will be talking about the nutrient addition. So here we're again looking at the cycled cases, but looking at the difference between when we added daily nutrients and when we didn't add daily nutrients. What we do see is when we add daily nutrients, it actually reduces the oxygen production rate over time. And I'm going to get into that a little bit later. But what we see for photosynthetic yield is that with the addition of daily nutrients, it doesn't necessarily give us a better photosynthetic yield. And also we see in terms of growth that adding daily nutrients seems to inhibit growth. And one of the hypotheses of this is in order to have daily nutrients or to do your daily nutrient addition, you actually remove some of the culture. So there's the possibility that the removal rate is actually faster than the growth rate of the algal culture, which could then speak to why we saw such low oxygen production rates as well as growth rates. But that wouldn't necessarily influence the photosynthetic efficiency or the photosynthetic yield rates. So for the eugenic versus contaminated culture, we did see that contamination status is not a factor for the cycled cultures. We did see a drastic drop in photosynthetic yield for the cycled cases, but we did see a reacclimation or acclimation. We saw that the contamination cases, the cycled one, did grow faster. We saw that the non-added cycled case had a higher oxygen production rate, explained maybe why that is. We saw that all the cases trended together for photosynthetic yield, and that the non-added cases grew faster. And we explained that that may be because our addition rate was faster than the overall growth rate. So overall, it showed that a minimally fed dirty culture will be just fine in temperature cycles. So what that means in terms of spaceflight operation is the crew doesn't need to interact with the photobioreactor that often, and they don't have to worry and stress over whether the culture is clean or not, because it'll be just fine. Moving on to the CO2 cycling. And the reason we took a look at that is inherently everybody has cycles in their CO2 concentration due to respiration. So depending on the type of activity that you are conducting throughout the day, you're going to have a different level of CO2 concentration. So this is a snapshot of 48 hours of an astronaut going through nominal sleep exercise. So here we had more of an experimental objective, which was to characterize the effect of dynamic carbon dioxide concentrations on growth rate, photosynthetic quotient, carbon fixation, and nitrogen fixation in chlorella. So I was able to use gas-tight cookie containers, modify them so that they could hold my pH, dissolved oxygen, temperature probes. This was a sparge unit, so I had gas with concentrated carbon dioxide flowing through the bottom with a exhaust port coming out the top. And I had this inside of the environmental chamber, so I had constant temperature, constant illumination, and I was using a contaminated culture, chlorella culture. So I had 5 different carbon dioxide concentration cases. So I had 3 levels of carbon dioxide, low, medium, and high. These were scaled down from the astronaut respiration concentration cases because my gas analyzer could not detect at such high levels. So with the lessons learned from the stagnant cases, and then also went ahead and did step function cases. So I did a low concentration to a high concentration step, and then a high to a low, in order to check for system hysteresis. So I went ahead and measured specific growth rate. Now, specific growth rate, you have to take a look at the exponential growth phase in order to capture the specific growth rate. So taking the cell density or cell count and plotting it on a semi-long plot, you can see the linear aspect is what I focused on. And so from that, we were able to calculate the specific growth rate. And what you see is in the low to high case, we don't see a statistical difference or significant difference in the specific growth rate as you go from low to high, but you do see a difference as you go from high to low. And you see a similar trend in the photosynthetic quotient, that as you go from low to high, you don't necessarily see a significant difference, but you do see it in the high to low case. For carbon fixation, you actually do start to see changes in the low to high case. As you change your CO2 concentration, you do see a very significant increase in your CO2 fixing rate. But on the other hand, you see a stagnation in your high to low case. And then for nitrogen fixing rate, you see a decrease in your high to low case, and then a stagnation in your low to high case. So what does this mean? Well, we saw that the low to high step typically results in almost no significant metabolic change unless it's in the carbon dioxide fixation case. And that in the high to low step, we did actually see significant metabolic changes, typically in the form of a reduction. And what this means is, if we were to use this in a dynamic environment and we had a sudden increase in carbon dioxide, the culture may not actually be able to respond fast enough. Typically, we need things in the order of hours, not days. But on the opposite side, conversely, if we were to have a reduction in CO2 provision, say we all go to sleep, the culture would be just fine over the next few days. It would be able to acclimate. So we have a culture that adapts to changing carbon dioxide concentration. And I just want to say a special thank you to Series and Dr. McCutcheon's group for lab space and helping me out with the carbon dioxide and nitrogen fixation measurements. So finally, we're going to be looking at heat mass transfer across a non-porous membrane. So I used a non-porous membrane in order to provide CO2 to my apple culture. And the reason I did this is typically here on Earth, we use a sparging unit, so we use bubbles in order to transfer carbon dioxide into a liquid stream. And you can't use that in a microgravity environment because bubble formation is chaotic and sometimes problematic. So we use this gas permeable membrane because it's concentration driven, meaning we have a lower concentration of CO2 on one side of the membrane than on the other side. That, let's say, carbon dioxide, that carbon dioxide will actually travel through the membrane into that lower concentration area without bubble formation. So in my test case, I had water flowing on the outside of the lumen or outside of the fibers. I had nitrogen with carbon dioxide and heat flowing through inside the fibers. And because I had a lower concentration of carbon dioxide in the water, I had carbon dioxide and heat flowing into the water stream. So what left the lumen was a carbon dioxide and heat poor gas stream. On the water side, I had water that had oxygen. So since the gas side did not have as much oxygen, I had transferred into the lumen of the fiber. And what left the membrane module was water with less oxygen. So then overall, I had water with carbon dioxide and heat, and I had nitrogen with oxygen leaving the membrane module. And the reason we thought, or we hypothesized that we could also conduct heat transfer with this particular module is because if you look at kind of the heat exchange diagram, it looks very similar to the membrane module that we used. Also, industry currently uses membrane modules for membrane distillation, which requires heat transfer. So our hypothesis was that mass transfer would be dominated by fluid flow, and this is because of the dominance of diffusion, or basically eliminating diffusion of gas into liquid, while heat transfer is dominated by gas flow. And we can see that through specific heat values in gas and in water. Carbon dioxide will have a higher rate of transfer with the cold liquid temperatures. Once again, looking back at solubility values, and oxygen will have a higher rate of transfer from the warm liquid temperatures, again, due to solubility. So this is oxygen removed. This is oxygen that's moving from the liquid side into the gas side. And we had data provided to us by the membrane producer, PermSelect, and that's in the solid line. So we replicated the experiment from that solid line so that we could characterize the membrane modules that we had purchased from them. And that's the open icons that you see. But then we conducted our thermal loop experiment using colder water, and that's the resulting oxygen transfer on the lower side, the closed icons. One last note, what we see is our hypothesis is supported that the gas transfer is dominated by the fluid flow. And then in terms of the CO2 transfer across the membrane, we also saw that we had a dominance in fluid flow in terms of how much CO2 is transferred across the membrane. The CO2 is going from the gas stream to the liquid stream. But we also see something else. Because it is a gas stream, gas going into the liquid, we see some influence by the gas flow rate as well, which was unexpected, but it does make sense. So finally, for heat transfer across the membrane, we do see that gas flow dominates that heat transfer as expected. So as we saw, mass transfer is fluid flow dependent, heat transfer is gas flow dependent, and we saw that the oxygen transfer rate positively correlated with fluid temperature as we expected. So what does this mean for the overall system going forward? Well, if we want to have mass gas transfer, we need to make sure that we have minimum fluid flow rate. And if we want to have max heat transfer, we want to have maximum gas flow rate. So let's put this all together. So for this combined membrane tubular reactor, this is the first version that I made down at Kennedy Space Center as part of one of my VTEs, Visiting Technology Experiences. And this is kind of a misleading photo because this is my first day photo. 3 days after this, everything's dead. And part of the reason we think that happened, we hypothesized, there were two main hypotheses. One of them was that cleaning protocol that we talked about earlier. We were using a hydrochloric and bleach rinse. And what we were thinking is that in all those little cracks and crevices that you see, the bleach was actually leaching into those and not being rinsed out, but then leaching back out in the culture later. But then also, each one of these bioreactors is 5 liters. That membrane system that we just took a look at cannot support that level of volume. Those membrane contractors really can only support about 1.5 to 2 liters, so more like this side. So going forward with those lessons learned, we went ahead and developed a new vertical tubular reactor. The reason it was vertical is because we had constraints by the dimensions of the environmental control chamber. We would have liked to have had horizontal so that we could minimize the effects of gravity both on the culture and the unit. But you get what you get. So we have the vertical tubular reactor, which I'll go ahead and pass around because I don't know, it's cool. But what we did is we actually had our illumination unit, the fluorescent bulb, going through the center of the reactor. And that way we could capture all of the illumination provided by the festival. Sorry, John, I'll actually do that community first. But we went ahead and used the water chiller in order to induce those temperature cycles on one of the units, since we have both a control unit and a temperature cycle unit. And then we also included the membrane contactors for gas provision. This experiment also had just a general overall objective, which was to identify the potential failure modes and operational difficulties with this particular system while characterizing culture support. So this is oxygen production rate between both the controls, so that's that constant 19 degrees Celsius, and the temperature cycle unit. And interestingly enough, we see a lot of variability in the oxygen production rate for the control, and not so much for the temperature cycle. At this point in time, there isn't necessarily a hypothesis of why. I do know that some of these jumps are a result of increased carbon dioxide. Unfortunately, we had some lab-made interactions with the unit, and so in certain cases, 100% CO2 was being provided to the system instead of the lower concentrations we were hoping for. So that happened at 5, 13, 14, and then as well as at 20. But interestingly enough, after those spikes in CO2, what you do see is this increase in provided oxygen. So you do see that the system is responding to these increases in CO2 and then dropping back down. But unfortunately, it seems as though they get used to that increase in CO2, but then have to reacclimate themselves over time. Another unfortunate thing about this particular system, or lesson learned, is that the membrane filters out biomass. So over the course of time, we saw a drop in optical density. So when we opened up our membrane unit, we saw all this biomass. But interestingly enough, we end up at this plateau right here. And if you look at the spectrophotometer manual, it says that it can read even lower than that, which shows that we actually are reading some amount of biomass constantly in the liquid stream. So because we filtered out all that biomass in the membrane, what does that mean for our gas transfer and our heat transfer? Well, for the heat transfer across the membrane, we didn't see a significant delta across 25 days, which was encouraging. However, in the heat transfer side, the model estimation that we have shown was based off of not having any biomass present. So that was based off of those previous experiments. So additional experimentation should be conducted in order to understand the influence of biomass on heat transfer rates. What we see here are two significant levels of heat transfer, but there really isn't a defined trend. So what does this mean? Well, the system was able to successfully support culture for at least 25 days. You can see that both in the oxygen production graph and also in the optical density graph. The membrane filtered out the biomass, but still was able to support it. But that biomass did not affect the gas transfer that much. And we don't quite know at this point in time how it affects the heat transfer, so it does require additional investigation. So, just quickly going over the feasibility of the system. Again, we have a temperature cycling experiment and a combined experiment. So I conducted a literature survey, and what I found was with a unit operating at its highest efficiency, with a particular set of elimination and carbon dioxide concentration, we're looking at needing about 1,300 liters in order to sustain a crew of 6 for oxygen production and about 2,200 liters for carbon dioxide reduction. But like I said before, this is using optimal conditions, so we may need to isolate the thermal control side from the aerovolization side, where you only have a certain amount of algae that is flowing through the thermal side. Now, for the temperature cycling experiment, unfortunately, because it had lower upstream production rates, what we see is we do need a lot more volume. But if we compare my experiment to the literature experiments, I wasn't using the most efficient illumination spectrum. Sorry? Yes?
Just a quick question. What is the unit DM?
Dry mass. Dry mass? Yeah. Yeah, it is, that's pretty standard, but I just wanted to make sure that if I said grams, I didn't have the biologist asking dry. But what we see, what I realized is that I wasn't using the most optimal illumination, and I was using a lab concentration of CO2 instead of 5% or 10% like the literature studies were using. So if we were to increase both of those inputs, there's a possibility that we could reduce the required volume. And then the same thing with the combined experiment. Also, there's the potential that instead of having the entire membrane system with the vertical reactor, why don't we just focus on the membrane and eliminate the membrane, which some systems are actually looking at. So this was actually an interesting experiment. It was kind of outside of boundaries, but I hope that with the results that you see here today, it encourages NASA and other space organizations to look at other species besides chlorella and spirulina. Because Antarctica is known to be a harsh continent. That's kind of the tagline there. And it's already used as space analogs or for space analogs. And it's a misnomer. A lot of people think that because it's a polar desert, that there's absolutely no water, which is not true. So you see here, this is Taylor Glacier with white falls flowing into the Bonnie. And then you have Lawson over on the left-hand side flowing into the Bonnie as well. And because there's liquid water, as we know, that means that there's got to be some sort of life around. And there is. So here's a picture of prior desiccated algae. This is algal math has been freeze-dried. So what happens over the winter months, this algae basically freeze-dries, preserves itself, and then comes springtime when the glaciers start to melt and the streams start to rehydrate. That algae becomes wet, and within about 15 to 20 minutes of rehydration, it starts to photosynthesize again. And I think this is just the coolest picture because this is algae in Antarctica that is producing so much oxygen, it's saturated in producing bubbles. And this is in 9-degree Celsius water. So I was able to sample algal mass from various creeks and streams across the dry valleys. But today I'll be focusing on samples that I gathered from Wangara Stream. And in part because it has had the most consistent green algal growth throughout history and survey history. So the hypothesis is that temperature cycle Antarctic culture will have an increased oxygen production rate and photosynthetic yield when compared to chlorella culture grown in the temperature cycle environment or in the constant cold environment. It's one of the environments that I didn't touch on in previous experiments that we conduct. And what I need to say is, at the time of making these slides and publication, we had only conducted one run of this experiment. So this is preliminary data. I cannot make statistically significant conclusions, but what I can say is this does suggest some pretty unique things. So if we were to try and supply oxygen for crew 6, I'm going to try and put it in terms of people that people can understand, we would need about 3 kiddie pools worth of it. But you need 6 if you were to use chlorella for temperature cycle case. I think what's also cool is for the Antarctic green mat experiment, I was actually using colder temperatures than that of the temperature cycle experiment with chlorella. And what we see here in the photosynthetic yield, that when you use colder temperatures with a chlorella culture, you actually reduce the overall efficiency of photosynthetic yield of the culture. So that suggests that the Antarctic algae are more robust in these colder temperatures. So if we're trying to use it for thermal control, or we need it to be at these colder temperatures, we really should be preferring these Antarctic cultures. So some main takeaways from this preliminary data, we actually have a slower growth rate, so we have a longer acclimation period with these Antarctic species. So typically, chlorella will start to acclimate, basically rebound after about 4 days. Here it takes about a week. But if you use cryodesiccation or use that freeze drying to take preserved samples with you to your final destination and rehydrate them so they're already at their final desired density, that might not be an issue. We also saw higher photosynthetic yield, and we also saw a higher production rate when compared to doubling samples of chlorella with a cool temperature chlorella. So what this tells us is that we really should be giving these species consideration when looking to use bioregenerative technologies for Martian locations. Again, I would like to make a special acknowledgement to the McMurdo Long-Term Ecological Research Group, especially to Dr. Diane McKnight and Dr. Michael Russo. And the MCM LCR is supported by NSF. So, final conclusions. Revisiting the research hypothesis, I again was looking at an algal system's oxygen provision, carbon dioxide reduction, the adaptability of failure modes, and seeing if it made it feasible for long duration spaceflight when compared to the current air valorization thermal control access. In order to do so, I looked at the following 6 objectives. So I was able to investigate through a literature study the reliability of the non-deployed bioreactor. I was also able to look at the influence of temperature swings on an algal system, CO2, and oxygen generation. But the reason I gave it an orange check mark or a reddish check mark instead of green is because I would have liked to have conducted more experiments in order to establish higher statistical significance, but wouldn't be all. I was able to quantify the consequences of time varying CO2 or those dynamic CO2 swings or concentrations. Again, giving it an orange check mark because I was only able to do the step changes instead of the cycles like we saw in the later slides. I was able to characterize the simultaneous mass transfer and heat transfer across the non-porous membrane. I went ahead and developed and produced a benchtop photobioreactor system that's gravity independent. Unfortunately, I had some difficulties with the algal support, but it leads us to maybe want to use the membrane-only portion of the system. And I was able to determine first order feasibility with the results of the previous experiments. So again, when comparing my system, my proposed system, to the ISS system, we see that the future of algal bioreactors in space looks relatively promising. We saw that algae is tolerant to these off-nominal conditions, that they are able to acclimate, and they are able to rebound or basically come back and support humans in space. So just a quick look at the TRL level. I took it from a TRL2, which is basically equations only, back of the envelope kind of calculations. then able to move it up to a TRL4, which looked at benchtop testing and component testing. So for the future work, again, I would really highly encourage NASA, if you are listening, please look at investigating cultures in space analogous environments. You would not want to try and use something that is not adapted or suited for a particular environment. You should be using a thing that's already there. Also, to continue to look at membrane-based flow bioreactor research, because I do think there's a promise. We saw that even though there was biomass buildup, we still had efficient mass transfer and heat transfer. Look at new integration methods to scale mass power, and volume. And this could be anything like 3D printing agar so that we could embed algae onto different surfaces or what have you. I have ideas, come talk to me. And also improve gas provision as our illumination systems improve. So I'm talking about improving LEDs. Well, if we improve our LEDs to a certain point, we need to also make sure that we are providing enough CO2 in order to support that illumination. As we saw in the previous curve, we don't want to become limited. And benchtop is a good start. And I think Tobias can also speak to this one, but more specifically, heat is required in order for us to establish the operation of these types of systems in a microgravity or reduced gravity environment. So with that, thank you for listening. I would like to thank my PhD committee for sticking by me for the past 35 years. I would especially like to thank my advisor, Dr. Nabi. He took a chance on me being one of his first PhD students. He knew almost nothing about me when I first walked into the office, but still was willing to take me on and say, all right, we got no funding, we'll figure it out. So it got us here today. So hopefully, with the body of research that I produced, it actually helps you advance your lab. So, and with that too, Dr. Torrin Clark, Dr. David Klaus, thank you for leading me through the bioastronautics department and helping me establish what human spaceflight means. Dr. Daniel Barta, thank you for helping me navigate my way through NASA as well as your own biological experience. And Dr. William Lewis being very patient with me while I try to learn about animal systems. And finally, too, the department to Biosphere, basically treating me as one of their own, letting me come in, use their equipment, and supporting me in any way that I thought I needed, didn't need, but still got. It was amazing. Thank you very much. Joplin Space Center and NASA Ames for supporting my BTEs, and Kennedy Space Center as well. To Ceres for helping me be able to conduct my experiments. Dr. Pat Selleck, who first introduced me to the Antarctic species. So, Dr. McGrath, I don't know if you want to blame him for that or not, but no, I'm very appreciative of him. He too has been very patient as I have learned more and more about algacultures. And to the McMurdo LTDR for allowing me to come along and help support their science endeavors, but then also learn a lot along the way and use it in my own research. And then to my undergrad too, who has been able to take some of the burden off and let me do my own thing while she's been continuing on with her measurements. And then to my family, especially my husband, Andrew, he has been very, extremely patient. Very, very, very patient. Thank you. My mom and dad, my brother John, who has kept me sane over the past 3 months. My parents-in-law, grandparents, and uncles, cousins. Especially the friends, Tom Vance, who I've known since elementary school, and who introduced me to Art Man. And so anybody who knows Art Man is like a brother to me. Jordan Lopez, who took me by the ankles and basically dragged me across the finish line here. And really anybody who over the past couple of months checked in on me, said good luck, provided equipment, provided support. It means more to me than basically love. So, thank you. And with that, I will go ahead and conclude and take any questions. Oh, good, no questions.
So it's about 10 o'clock, but let's have 5 minutes or so for any questions from the audience.
Denise.
Great job.
Thanks.
I was wondering what a gravity experiment is. What does it mean for this to be gravity?
So I'll go ahead and repeat the question. You let me know if I heard it correctly. So you said, what is a gravity independent experiment?
So you said some of your experiments were like with gravity and fire.
Yeah. So gravity independence basically means that it isn't relying on things like Brownian motion or density gradients in order to move mass across different mediums. So in this case, the difference between a gravity-dependent system and gravity-independent system would be like sparging systems, using the bubbles to bubble up, because you are relying on the difference in densities of the gas and liquid in order to push the gas through the culturing unit. But the membrane, because it doesn't rely on that density difference, it doesn't need that. So, yeah. Did that answer your question?
Yeah.
Or, Mike?
So a few slides back, it said something like a few tons of liquid
Yes.
for everything.
Yes.
I'm just wondering if you can compare that against like total mass of combined mass of seagrass, body and whatever comparable LTL components.
Yes, yes, I have. And that was part of the first one, the feasibility study. I just didn't think that those numbers necessarily would be very sexy. So, but the publication that I do have listed at the end of that particular section does have those numbers there. Okay.
We experiments conducted in connected to environment contact.
They were conducted in a nitrogen environment. So in most cases, I was using basically lab air or shop air in order to provide the buffer gas, in which I then increased the CO2 concentration.
And that be the same environment you would experience in say, the National Space Station?
Yes, yes, typically it is, typically you would use an ambient environment condition, and the CO2 concentration that you would have, the increase in CO2 concentration would be provided by human respiration. So.
Okay. Thanks, Emily.
All right, thank you.
And at this time, yeah, go ahead and speak. And at this time, I'll ask the audience to leave, and you can take some treats or coffee on the way.
Yes, please do. Please.